And there we are.
There we are. We are live. Great. Perfect.
And
hmm
is there anything we need to do on LinkedIn Live to make that work, or is that off and running?
it is off and running.
Beautiful.
Wow. The power of technology. So I think we are getting in there. So everybody should be joining us soon enough on LinkedIn. Because I know there's a little bit of a delay in terms of how, technology again, how technology works, which is, I'm very grateful for technology and how it works because it actually works.
Yeah, I've seen when other people are doing a LinkedIn Live that it
hmm
comes into my feed with like
Right?
the
Right.
red status, and then I can click it and go. And
Yes,
yeah,
yes.
so
I'm now getting like the notifications of, you know, we're live, it's time to go. So I think people will start coming in very slowly and just get in. So I just want to make sure that we have the people joining us and
sure.
they are, getting into where they need to be. And I'm
So,
checking in because I'm seeing like the LinkedIn people are just jumping on slowly, slowly but surely. Slowly but surely. So they are just jumping on there. And I know on the YouTube side, we have some people joining us as well. So we're trying to cover all angles.
yeah,
Everybody who needs to see and learn some more about crease analysis. Because, of course, that's what we're going to do today. We're going to talk some more about that.
yeah,
But I think it's like a very exciting topic because oil gets all of the traction, you know. Everybody's like, "Oh, let's talk about oil." But grease is also a very important part of it. And
sure.
it's the most overlooked part because nobody wants anything failing. And when something goes down because of a grease failure, it tends to give that, spin off effect where other things start going wrong. So, being able to understand what's going on with your grease at any point in time is actually pretty good. So, that is one of the purposes of our sessions here, making sure that we have more people involved, getting more people to understand more information about grease analysis because it is an area that a lot of people forget about. Like clearly they forget about it.
Yeah.
But
Now, we talked about recording this. Now, to your knowledge,
mhm,
is this recording then in this new StreamYard,
I
or is it
believe
just in the YouTube?
it will record in YouTube. So we will be able to send that link out to everybody on afterwards. They get the YouTube link. They could play it back because I know we're dealing with different time zones here.
Sure.
So it's always, that bit of trying to find that spot that everybody could join. And if you can't join, we will find you. You will find us on YouTube. You'll find us on LinkedIn. I know Hamza is with us as well. You
Great.
know, thank you for joining us, Hamza. Always appreciative that you can jump in with us. And we're trying a different platform this week, trying the LinkedIn and the YouTube versions just to make sure that we get the message across, we get more people involved because this is what you need to know about grease analysis. And I know today we're talking about motors
Yeah.
and all of the motor operated valves. So that is, it's always a good thing to start talking about that because every single plant has that in it. Like, yeah, you can't go to a single plant and it doesn't have a motor in it. Not even a plant, like most operations, like everything has a motor in it.
Right.
I hear a motor outside because, it's whatever, but motors are everywhere. And being able to understand like what's going on with the grease in that can actually lengthen the life of your motor. And a lot of people, motors are expensive, guys. Like getting those when those go down, those are like the workhorses of your factory, you know. So that's one of the things that you want to make sure that they are actually, you know, working properly and that you can make sure that you extend the life of your motors. So,
Yeah, and I think that more recently, with supply chain issues,
oh
sometimes certain
yes.
motors, especially larger motors, have
Mm-hmm.
become more difficult to get in a timely manner. It's
Yes.
very
Yeah.
expensive to keep stock there. So if you can understand how your motor is doing and kind of project out when what your needs will be and so forth, that's certainly going to be helpful. In addition to just extending the
Yeah.
light, the investment that you made in those motors. Um, and so, what I'm going to share today comes from a conference I was recently attending called the Machinery Failure Prevention Technology Conference that was recently held. And so, I'm going to build on that. In that conference, we focused on motors, but also motor operated valves.
Mm.
Motor operated valves have a key role that they play in the petrochemical industry, in nuclear power, as well as certain marine shipboard type applications. And so it was really, for that audience, really where we wanted to be. So what I can do is if you're ready, I can bring that
Oh yeah.
presentation up and we can get going.
Oh yeah, for sure. The
Yep.
stage is yours, Rich.
Okay, super. So yeah, I'm going to talk now about optimizing lubrication for motors, the motor operated valves, and I throw a few components in at the end as well that I think are really good examples of how we use grease analysis to optimize lubrication. So let's get into it. Motor grease lubrication starts with the selection of the proper grease, which is base oil, its viscosity, the additives that are
Mhm.
required, and then the NLGI grade. So it has to be correct for that application. Then we have to choose how often are we going to be replenishing the grease. Unless it is a sealed for life bearing, there has to be some frequency of replenishment. And how do we determine that? So we'll talk about that a little bit. We also have to decide how much grease are we going to add each time we go to replenish it. And we'll talk about how you determine that. I'll mention the risk of grease mixing, what can happen there, and how that can be driven by supply chain disruptions or products that are discontinued, which is something that's become more frequent in recent time. I'll talk about the challenge of purging grease, and then I'll mention sensors, the
Mhm.
role that ultrasound can play there, grease sampling and analysis, and then in situ grease sensors, which is kind of a brand new topic that
Yes.
I'll introduce here today. Um, so let's start by talking about controlling the volume of the grease. If we've got the right grease, we've gone through that process, we got the right stuff, like how can we control the volume? And unless we have an active program that either is prescribing specifically how often, how much, and it's a very well known requirement, we usually end up over lubricating, and you see this all the time in failure. And so one of the more recent technology additions to the world of greasing that has been very effective and is really growing is ultrasound greasing, or using ultrasound technology to control the volume of how much we're greasing. And when you talk to the folks who build that equipment, who are selling ultrasonic greasing solutions, some of them will say that is now the biggest part of their market. That's the fastest growing segment of this, ultrasonic monitoring, which is pretty exciting. What it does is it detects asperity contact due to an inadequate film. So we call that in a rolling bearing the EHD film, the elastohydrodynamic film. And if it is insufficient to separate those surfaces, now those little peaks of roughness on the surface start to hit into each other. And that sends off an ultrasound signal that can be determined. So the first thing it helps us look at is there an adequate EHD film to prevent those asperities from touching? The second thing it can listen for is grease churning. So if we start to add too much grease, that volume, that decibel level starts to go up. And then you hear that in the ultrasound, and you can look at that in the numerical values. The third thing we use it for is bearing damage. And so even if we add a whole bunch of grease, it doesn't make damage go away. And so we can continue to hear those bearing frequencies. And some ultrasound technologies, you can actually dial in the bearing frequencies, the ball pass, the inner outer, the ball spin, all those frequencies, and kind of align them with the ultrasonic measurements you're taking really help us diagnose. So, three important things. Do I have the film? Have I added too much grease? What's the condition of the bearing? Now, in the absence of that technology, or a lot of times being utilized alongside that ultrasound technology, is calculations to determine what should my replenishment intervals be. And this section here talks about some calculations that Amory has put together, and they have developed a tool called the Lube Coach, and the Lube Coach helps you calculate what should be my frequency and quantity and so forth. You can see there's multiple steps before you get here. You got to have the right grease. You got to know the grease is right for the application. And somewhere down the line, step 7 is how often do I add the grease? And it's a combination of the shaft speed, the size of the bearing. So together, the shaft speed and the size of the bearing give us the angular velocity of the rolling elements. And that value is then modified by all of these adjusting conditional factors, which includes temperature. So the hotter the bearing is, the hotter the environment, the hotter the grease gets, the faster it'll oxidize and need to be replenished. And so you adjust for temperature. There's also vibration levels. If you have a machine that vibrates, say it's a vibratory screen or something like that, that vibration actually shears the liquid from the grease, causes it to run out and can dry out the grease. So if there's a lot of that, you want to grease more often. So there's an adjustment for that. There's contamination adjustments. If there's large amounts of particulate, especially abrasive particulate, or moisture present, you need to grease frequently enough to push that out, to purge those contaminants so they don't get to reside in and build up in the pathway of the rolling elements, because that leads to abrasion and fatigue. There's also a factor that's related to the type of bearing. So a ball bearing is kind of the mildest damaging bearing type, if you will, to the grease, because it has a smaller profile along that raceway. But if you have, say, a tapered roller bearing or a spherical roller bearing, it's like a steamroller, and it's smashing through that grease and it's breaking it down more often. So you'll see adjustments, whether it's a ball bearing. Typically, if all your conditions are the same, it's a ball bearing versus a cylindrical roller bearing, you'll grease the cylindrical bearing more often because the grease gets beaten up, its consistency runs out. And so there's all these calculated adjustments that we can make. You can find them online. SKF has a calculator that you can use, skf.com. Amory has the Lube Coach, and there's other sources as well. So that's one way to calculate out how often I should be changing or adding or replenishing the grease. I'd like to mention mixing the greases, and I may have shared this slide before. It's one of my favorites. It comes from the National Institutes of Health when I worked there, and it was this failure of this bearing, and I was told to investigate it, and I was told the bearing rusted out. And you see this reddish dust on this bearing, and you can see where that comes from. But of course, the story that I tell is I saw some grease residue. I captured that grease residue using a grease. We analyzed it, and what we found was the lithium complex grease that was supposed to be there, along with polyurea grease. They had mixed together. The oil ran out of that thickener, and it starved the bearing. And now you've got metal-to-metal contact, and you've got oxidation. So that's one of the key risks that we're worried about with mixing greases, is actually losing the lubricant and having that catastrophic failure. Another one is the grease can harden in place. And as it's hardening, it's more resistance to movement of the bearing. Some greases almost become like a rock. And not only do they block new grease from getting in, but they also can kind of retain or constrain the movement of the bearing, causing overheating and other problems. So all these things can lead to machine failure. And that's why one of the things we want to get a handle on is around mixing greases. And so I talk about the compatibility charts, and my general statement here is they're bad and wrong. okay, in that order. And they're really a bad idea. There's many of them out there. I did a study for Noria's magazine, Machinery Lubrication, a few years back. I did a search of the internet. I found 17 different compatibility charts. They did not agree with each other. There was no reference testing listed that was used to create them. They did not account for the base oil differences. They don't account for the additive differences. All they say is if you have this kind of soap thickener or non-soap thickener, these two are compatible and incompatible. And even that isn't always accurate, because if I say in a chart like this that I've got a lithium complex grease, I really haven't narrowed it down. There could be hundreds of different fatty acids used to create the chemistry of a lithium complex grease, all of those different combinations. So we know that no one has tested all those combinations. And so these generic compatibility charts are really not a good idea. They really don't answer the questions about that. So what we have as an alternative is a compatibility study, right? And we've talked about this in some of the earlier meetings that we've had here, but it allows for the evaluation of mixtures without risk to equipment or affecting the uptime of that machine. And especially if we know it's coming, right? If there's a discontinuation of a product, or maybe corporately a company decides we're going to buy all of our greases from this and oils from this company, that means whatever's already out there is going to get a new partner in there. So we can get ahead of that by taking those mixtures and testing them in a compatibility study. And it helps us assess the risks and costs and even look at available alternatives. And I've done this for some folks where we've gone through, hey, check this mixture of these two greases, fail. Check this one, fail worse. And then a third one, terrible. And then finally, the fourth one is the match. And so then they can just transition from grease A to grease B and not have the risk of a failure. But if you proceed blindly, that risk is quite high. And so the study is the 6185 ASTM D6185 is the primary testing. It uses three standards. That's the way which it is currently written. It gives you the 1090 mixture, the 5050 mixture, and the 9010 mixture of those two greases that you're using to compare. And then it looks at dropping point, shear stability, and storage stability. And it does say, and a lot of people stop right there and they say, oh, I've tested those greases, I did those three things. But it does say in this method, if it passes that primary testing, or if you have a specific, application, there's other secondary compatibility tests to evaluate it further. And this method is really under review right now anyway, because there's some concern about it's just a little too simple. In fact, if you look at dropping point, shear stability, and storage stability, those ASTM standards say these do not predict in-service performance of greases. So why do we want the tests that don't predict the performance to tell us whether two products are going to be compatible when they mix together? So there's some other things that we do. We work the mixtures, and the current standard has this grease worker does the 10,000 double strokes, which sounds like a lot, right? Boy, that's really mixed up. But the thing to remember about that is that physical working isn't just to get like a homogeneous mixture. It's also to break down the grease in the same way it will be worked when it's in the bearing. And if we look at that 10,000 double strokes, it's really equivalent to 93 seconds of working in a typical electric motor bearing. So is 93 seconds enough to know whether those grease mixtures are going to hold up? I don't think they are, and that's why we do it a little bit differently. We spend 72 hours in a bearing simulator. So we pack these two mixtures of greases into the bearing simulator. We have 8 bearings in the simulator. We put the neat greases or the unmixed greases in other bearings. They get worked at the same rate. And then we compare what happens to each of the greases as well as the mixture. And it ends up being around 28 million mixing events as opposed to the 10,000. And the key there also is that what do we do from a results perspective? And this is where we look a lot deeper into the results. And so on this, and I don't know if you're looking at a small screen, maybe you can click the button in the bottom and it blows this up a little bit better for you. But what we're showing here is the rheological properties of the grease. And more than just the cone penetration, which is like, how is it still a clump of grease that's going to stop a cone? These are the dynamic behavior measurements of the grease. How's it going to behave when a roller is going over it trying to make that film? Or is, as the grease, as the bearing pushes the grease out of the way, is it going to slump back in behind that roller, or is it going to form a solid wall and basically starve the bearing? So these indications, this G prime, this yield stress, and this recoverable compliance, actually give us those varied dynamic, what we call viscoelastic behaviors of the grease, and help us predict, does this mixture behave like the individual greases, or does it go off in a completely different direction? So you see down here to the right, here's the G prime values of two greases that have very different G prime values. And there is a numerical predicted value as the light blue. And you see the dark blue says, boom, right on. Those
Mm-hmm.
greases, when you mix them together, still behave like you expect them to. But if you look at the one on the left, two greases, very different G primes. The dark blue here is the expected, and it's orders of magnitude lower. So it's an extremely soft grease that's going to have a hard time staying in that bearing. And that's not what we want. We don't want that mixture that's going to behave dynamically in a very different way than the individual greases do. So this kind of test helps us figure that out. So these are the considerations. And then, we say, okay, we want to avoid mixing greases. We want to choose the right grease. We want to make sure it's correct for the application. But then how do we get a sample to assess all these decisions that we have made, whether we're using the Lube Coach or SKF or the OEM guidance? Like, we might not operate the machine exactly as is intended. We might have higher speeds, we might have higher temperatures, we may have vibration conditions. There's always going to be something a little bit different about our operating environment. And those guesses and assumptions and approximations may not tell us the story. So if we can take a sample of the grease while it is in service, even if it's just like at the end of our typical replenishment cycle, right? We add some more grease, get that grease that's coming out, and see what its status is. Does it have life left? Or is it shot? Are we late? Should we have been in there some time ago, months ago, replenishing that grease? So the first thing to figure that out and answer that question is we have to get a representative sample. And we've talked about this, and so I won't dive too deeply into it now because we've talked about it in some of our previous presentations. But number one, grease is sticky. It's designed to stay in place. The location of the sample within the housing, within the bearing, or if it's gears we're talking about, near the gears, that's everything. And the tools have to be able to extract from that target zone, not deliver grease from other areas, not new grease on its way in, not grease that gets put into the bearing and pushed off to the side and never really becomes part of the wear process or representative of the contaminants or whatever. We got to be in that live zone. So there are tools like the Grease Thief and the ASTM standard, D7718, which we've talked about, give us the tools and techniques. And then if we understand the flow dynamics, how does the grease get in? Where does it come out? How does it get moved around by the bearings and the gears? Where do we need to go? Once we understand that, we use the tools and techniques to get that representative sample. So what we wanted to spend a little more time on today was electric motors, motor operated valves, and some other things. So what about electric motor sampling? Well, the Grease Thief that we've talked about many times can be threaded right into the drain in place of a plug in many electric motors. There's an M10 thread for the metric side of things, and a 1/8 inch NPT thread are very similar. The thread spacing and things like that are a little bit different, but both of them can accept the Grease Thief. So if that's the drain on the motor, we thread that Grease Thief right in there like you see on this picture, and it's sitting there. It has a relief pressure that's 1 to 5 psi, and it's quality checked to do that. And then it can allow that grease to purge out. And instead of falling on the ground or falling down the side of the motor, it's captured separate from the environment, so we can see it. We can look right through the body of the clear Grease Thief. And then if we don't like what we see, we can unthread it, cap it, and take it to a lab for analysis. Or as we've been talking about, the mini lab, right?
Yes.
Do it right on site and get those answers right there because someone's scratching their head. I don't know. I'm putting a blue grease in. This kind of looks blue, but it's a little dark. Is it
Mm-hmm.
too dark? And the answer to that would be the grease leaf colorimeter. It'll tell you
Mm-hmm.
about how much the color has changed and whether it exceeds that threshold. Or is there wear? I don't know. It looks dark. Could it be because of wear particles? Then we put it into the ferro-Q, and the ferro-Q tells us precisely parts per million ferrous content. So that's what can be really helpful here. And then, the thing about the grease sampling, if we do it periodically, we can detect issues early.
Mm-hmm.
Hardened grease, for example, is a source of energy losses. And so that's a big thing with electric motors, right?
Yeah.
A lot of companies are looking at trying to demonstrate, what is the impact. And we can get actually, I did a presentation at the Noria conference last year where I actually calculated the carbon footprint of greasing activities and how much you can save, how many million tons of CO2
Right.
you can save by reducing the greasing frequency justified by grease sampling, right? The
Right.
sampling will say, let's optimize it. And I'll tell you what, Sandy, I've done this a number of times,
Mm-hmm.
and it's not always exactly the same, but it
Right.
all seems to average out that we're greasing about twice as much as we need to. If you look at the
That's
before and
that's a
after,
lot.
it's a lot. And then
That's a lot.
and then you look at, and so when I did the calculation for this, I looked at, what is the disposal costs for the
Mm-hmm.
carbon footprint of the grease? What is the mining cost of the lithium,
Right.
right? To make the lithium
Mm-hmm.
and calculate that all in. It's a pretty hefty footprint.
It is.
We
It
can
is.
take, yeah, we can take credit for that if we apply it. And at the very end of this today, I'll show you a case study for helicopters, which is quite
Right.
eye-opening and quite substantial. Um, so that's the electric motors. And while that last picture was a fairly, I would call it a medium-sized motor. It's not tiny. I think that one there was about 60 horsepower.
Mm-hmm.
Um, when you get into some of the larger motors, you'll have different size openings. And as the opening gets larger, where the drain would be, you can actually either use the grease thief with a T handle and go up inside and actively pull a sample, or you could use the grease thief slim or the new version that's coming out, the pickpocket, to go in there and take that little sample going right up through the drain and targeting that live zone in the bearing. But this one here is a passive sampling where you've threaded it into the motor, and then as someone comes along and adds grease, kind of mixes around, and then eventually a little bit comes out, and you're capturing that for a sample. So that's electric motors. Motor operated valves, these are prevalent in nuclear power plants, in petrochemical facilities, in ships, on submarines, and it's meant for remote opening and closing of valves, providing enough torque to get that positive closure when it's needed. So it's a critical functionality, and that's typically done by that transmission of motor torque to the valve closing force. And in this drawing, you see the motor there off to the left. You can kind of see the core in the cutaway, and then you see the driving gears in here. And then about halfway through, you can see there's a worm gear and then a stem that rises up vertically out of it. And it's that stem being forced down to close the gate or the poppet, whatever the valve design is. That's where the torque needs to work for this MOV to function as intended. But here's the thing: the torque is only related, the motor torque is only related to the closure force if you know what the lubrication is on that stem and the
Yes.
coefficient of friction. If it has a high coefficient of friction because that grease has degraded, then that motor torque is not all going to go into closing the valve. It's going to go into overcoming that coefficient of friction. So it really is important that these stem and stem nuts are greased properly, that the grease is maintained, that we know its condition, and that we have some opportunity to add lubricant when is necessary. So this is really, I like this picture a lot. It's a really
Yeah.
cool kind of view of what's going on inside. I mean, it's kind of simple, the functionality of it. You have a motor, the motor spins, the spinning motor turns the stem and drives it down, just like when you're at the sink and you grab that handle and you close the valve and you open the valve. It's just like it's a motor that comes out at a right angle and does that for you. So it's a really kind of neat design. And you can see kind of a cutaway of it here, that you've got a number of different areas that are being greased. You've got little Zerk fitting up here at the top, the upper bearing grease fitting, the upper left, and that greases that bearing. And then you've got the worm gear that's down here. You have a clutch ring. You've got a declutching shaft, and you've got the drive pinion that are running this, and they're all submerged in grease. And so all of that has to be functioning properly to get that transmission of torque. Now, it's been known and it's been demonstrated that stem nut can wear over time. It actually strips out the threads. And you can see the left you see the full threads there, and you see they're gone in that other nut on the right. And the nuclear power industry just happens to monitor these extremely closely, all the way back to 1993, when there was a special letter from the Nuclear Regulatory Commission that required all plants in the U.S. to monitor these valves regularly. And so they keep track of issues that come up. And they have identified multiple failures of motor operated valves due to degraded stem lubricant. 5 stem lubrication events, and there was a failure in 2011 due to a lack of lubrication because the valve stem was not accessible. So this is the problem. Like, how do you get, we're looking down inside of this, we see those threads, but that's typically filled by the stem. Yeah. So how do you get the grease down where it needs to be? There's no channel, there's no Zerk fitting. And what people do a lot of times is they raise that stem all the way up as high as they can. They coat it with grease, and then they run it down in. And if you've ever watched that operation, it leaves a great big pile of grease on the top of the nut. Hopefully drags enough down in there that's needed, but then you've got other valves that you can't do that. Because let's say the plant's running, I can't open that valve because all the water would run out of the tank. Or some valves are designed that they just barely move. They're just, might be a butterfly, or it just has a small stroke opening. And so in those cases, it's very hard to relubricate. Being aware that we invented the stem thief. And this is a tool so what you would see here normally is the stem kind of sticking up through the top of this blue area with a protector over it, just a pipe over top of it to protect those threads. But we remove that protector, and then we put this tool right on top of there, and it has an adapter here, and which is a pipe thread. So you see this darker iron adapter fitting, and then on top of that is this aluminum tool, and that has a straight thread. So now you spread that down, and it has the downward force to seal against an O-ring and make a chamber of grease. Then you can see the Zerk fitting right on top of this, right? All you need is a regular grease gun, and you pump that grease down, and it forces the old grease out. It runs all the way down through the threads, forces the old grease out, which you can sample and see what's the condition of that, but it reestablishes that layer of grease in there. So it works very effectively to do that. And we've had the chance to share the outcome of one of the major nuclear power plants. It's now in second place. It used to be the largest in the U.S., and the second largest in North America after Bruce Power. But now it's down to third place because of Georgia. The Vodal plant just brought 2 new units online. So, but still 3 large nuclear units there in Arizona. And they've had a number of issues in the past. So they purchased these stem thieves, different sizes, different configurations. They have 6 of them now that they use, and they're using them routinely, especially for the short stroking valves that just barely move because you can't get the grease down inside. And then they look at the coefficient of friction, and if it's trending up, they just use the grease thief and bring it back down again. And then they measure this with the torque. They know that this has made a significant change, which is great. It allows that testing and restoration to be done in a 2-hour window, and that means they can keep the plant running. This is a plant that is going to generate about $1 million a day. So start doing the math on that. It's significant. But they've been able to document the coefficient of friction dropping from 0.15 to 0.10. So
Oh.
a 30% drop, it's significant. So what about the MOV itself, the sampling, the old method? You get some non-active grease. There was EPRI research that was done, and the new method is this using the T handle. And here's what the stem thief kit looks like. Here's your stem thief in there, and there's some sampling tools that come along with it, help us monitor that. So we talked about electric motors. We talked about the motor operated valves. And once you got those samples, now what becomes our goals for grease analysis? Well, we want to evaluate the effectiveness of lubrication through wear quantification and determining what wear mode is there, right? Where are the particles coming from? And a lot of that's through analytical ferrography to see what wear mode. Is it abrasive? Is it adhesive because of a lack of lubricating film? Is it a corrosive wear mechanism? What's really causing that? We can also trend the consistency to ensure that the grease is still going to do what it needs to do, which is flow, get to the location, stay there in contact with those parts, and then be displaced when the new grease comes in to do that. We also measure the presence of the contaminants, and that can help us understand if our purging is effective, right? Remember when I said the frequency is determined by a lot of factors, and one of the factors is the particles and the abrasive particles. Well, we make kind of an assumption there when we look at our frequency, and it's based off of, is there a lot of particles, a little bit, are they abrasive, are they not abrasive? It's a bit of guesswork. So what we can do now with analysis is we can say, is it effective? Is our current practice that we have done, that we've set up for the amount and the frequency of replenishment, is it keeping the dirt away? And you'll see it in the grease. You'll see the particles. You'll measure the moisture levels. If it's not adequate, we increase it until we get that taking place. And by doing so, we're going to extend the life of our equipment. We can look at the grease for oxidation due to heat, due to being worked from the bearing and the gears, and the presence that the contaminants are a wear problem, but they also break down the grease as well. And then finally, we took the good sample, we did the analysis, we looked at all these different inputs. Now we optimize grease use by this testing and validating existing replenishment methods and adjusting them so it becomes optimal. And that's what our goal is. So we talked about the mini lab, right? The ferrous density, the colorimetry, and that is could be at the machine or in the field or in an office. It doesn't have to be in a laboratory. Just 2 quick tests that give us real insight into what's happening. If we see something there, now we can bump it up to laboratory grease analysis. Now we get down into doing those 9, 10, 11 different tests that are available to us when we get that sample back to the lab. But I also want to talk a little bit today about grease sensors. And I've shared here a new patent. It was just in December, this last December, about using grease sensors. And the challenge here has always been the physics, right? Because we might have oil sensors that work very effectively because we put them in the flow of the oil. The oil kind of flushes it away and kind of starts that process over again. But what happens with a sensor that you put into grease? The grease sticks to it.
Yeah.
And that's what you get. Guess what? A grease sensor rarely changes the measured parameter because it's measuring the grease that got stuck to it.
Yep.
So that's the challenge. This new U.S. patent and the developments from that are using a dynamic in situ sampling solution to introduce the grease to the sensors and then to release it back into the grease housing again. So it periodically pulls that back and forth. So that's an exciting new development, and we're looking to see that give us some more options for grease monitoring as we go forward. The tests that happen in the lab, that's D7918, the ASTM standard. And we've talked about some of these before. Wear metals can be tested by the FerroQ or by RDE spectroscopy. There are some labs using other techniques like XRF or ICP testing. There's some challenges there, but we've got some good methods that are in the ASTM standard. There's the consistency by that die extrusion method where we
Mhm.
squeeze the grease back out through that flow channel. We compare it to the baseline and we get a sense of, has the grease hardened? Is it drying out? Has there been a mixture? All these things can affect the way it flows and moves in the machine. We look for contaminants and oxidation by color. We can use the FTIR spectroscopy to look for oxidations, the presence of mixing, other contaminants. We can do moisture content down to ppm levels by using an oven and humidity sensor model. We can look for the wear modes with analytical ferrography. And then that ruler test, the
Yes.
time dependent oxidation stress by linear sweep voltammetry, that says when we came back and pushed new fresh grease in and the old grease came out, what was its condition? Was it shot? Were there no antioxidants left? Which tells us we waited too long, because we want to be displacing the grease when it's near the end of its life. We don't want the parameters to drop off. We don't want it to be degraded. We don't want to have an issue where it's perhaps not providing all the protection those surfaces need. And that's how we get to optimization. The analysis helps us optimize those frequencies. So we've seen these. I talked about them, in this presentation last week, but we've certainly talked about it quite a bit here with the FurrowQ and the colorimeter and what it's capable of doing, up to 200,000 parts per million. Uh, no spatial distribution errors, which some other instruments do have a challenge with, and gets us up to very large particles. I did share this about the MOVs. This is from a study, and by the way, anyone now is able to download this document. And I'm biased because I was one of the authors of it, but I think it's a really valuable document that was put together by the Electric Power Research Institute. But as time goes on, this is back in 2010. A lot of it is valid, still valid,
Mhm.
but it's no longer $25,000 a copy. You can go right online and download it. So if you go to EPRI, the Electric Power Research Institute, or EPRI.org, and then you go to the search window for
Mhm.
research, you can look for this report, or you can search it by effective grease practices, and you can download that. In fact, you can download it both in English and Korean translation.
All right.
Both are available. But one of the things that you find in here was the study that was done, which looked at MOVs. So this is an MOV, a motor operated valve, and we're doing cycles. We're cycling the the valve, like it's like opening the valve, closing the valve, opening the valve,
Right.
closing the valve. And what you see here is that at the start, the grease probably wasn't mixed up very well because the numbers were kind of jumping around, parts per million. But we took some initial readings that were generally fairly low with a couple outliers. But then we put a set of shims in on
Mhm.
one side of the motor. So we created a deliberate misalignment. So now your pinion gear is misaligned to the worm gear. And we said, what happens? And with the one set of shims, it didn't change too much. But when we added the second set of shims, that wear cycle, or that wear rate, went up substantially. So that told us two things. Number one is that we were taking a good sample at that point that's
Mhm.
representative. And then secondly, as that increase in wear happens in the component, it is proportionally detectable in that properly taken grease sample. And that was a big question at the time. It's like, yeah, we can do grease samples, but can't really shake it up like an oil
Right.
sample. The particles may be all over the place. Who knows? But this really helped answer that question and said, no, if you take the right sample, you can see that. You can see the change. You can see the increase. And we're not talking about a lot here, right? Just a couple hundred of ppm, but really clear in terms of the rate of
Yep.
change and that parameter that we want, to keep on top of there. I like to throw this picture in here, which is, I get to asking people, well, do you see anything wrong here?
Oh God.
But the two different color greases, this is something, again, I saw at NIH one time, and I'm sure somebody thought they were helping things out. Maybe they thought they heard a noise, squeaky wheel gets the grease, and they had to have a grease gun that was green, so they pumped that green grease right on top of that, amber colored grease, and that's potentially an incompatibility. So you could imagine when this happens and you take a sample, it's going to
Mhm.
be nothing like that original grease, and that's going to be very helpful. Over here, This is the output of the colorimeter, and you can see what a minor change and what severe oxidation looks like from a colorimetric standpoint for grease. And that's what we want to be able to do, monitor those things. This slide, which I think we've shared before, is just that kind of process of testing the grease thief, doing the ferrous, then the grease thief analyzer, and looking at the metals by RDE, the FTIR, and the ruler, all those things we do. But this leads me into the last part of this presentation today. And I bring up this case study. And I think it's a good one because from end to end, this was a lubrication optimization study. It was called the LOS, the Chinook LOS, lubrication optimization study. And this is an aircraft that's been out there for over 60 years. And it's still in production. They're just a whole bunch of them were just sold to Germany. And they continue to make these a very, very nice design. But there's this long history of maintenance going back 60 years. I was opening up manuals dated 1962 as I went through this study to figure things out. And what you see is that when you have a new machine design, somebody has to come up with a starting point, somebody's best guess of what we should be doing with respect to grease. There typically isn't the data there that says what's optimal. And as time goes on, we tend, and when I said earlier that, we usually use about twice as much grease as we need to, it's a natural human thing because if everything's fine, okay, no failures, what have you. But what happens the first time the grease doesn't look right? We have a failure. The grease looks kind of shot. Oh, grease more often. It's just a natural thing. Until we get into the state, we default into the state of over lubrication. This was no different. Over the years, when there was issues, failures, maintenance problems, when they would tear the equipment apart and find things that did not look good, it was often the response to say, well, let's shorten that interval. Let's shorten that interval. Let's get fresh grease in there more often. And the logic is, well, grease is not that expensive. So the machine is very expensive. So let's put some more grease in. But we now know that over-greasing is a problem as well. What we truly want to do is optimally grease all our components. And the only way to really do that is to test it. And so this is what we did for this study. We did this optimization study. We looked at historical field data. We had the participation of many different operators around the world. So they were operating in a lot of different environments. We took samples from bearings, some swash plate. Swash plate is the part when you have that rotor whipping around on a helicopter that changes its angle. It's a bearing that changes the angle and lets it be steered and go in different directions and so forth. And then in this design, you also have splines, and splines fit together as part of a drivetrain, and they're going to be greased. They have very small grease quantities there. But here's the field sampling workshop we did with some of the soldiers, and we had a custom kit. That kit is available now as the helicopter grease thief sampling kit. It follows the ASTM standard. It allowed us to transfer small quantities off of those splines. And even today, within the last few months, we've developed a new tool within the grease thief kit, which fits right onto the grease thief. It creates a little cup that you put the grease in, it transfers it right in, as opposed to these large syringes that we used in the past. So we've actually reduced our plastic footprint for the grease thief kits. We've reduced about 60% of the plastic involved in that kit with this new design. But here's what the kit looks like, or what it did look like. And of course, you're trying to get it all into the grease thief there. We focused on 7 tests that were part of ASTM D7918. And you can see some of them here, the different metals tests, ferrous debris, the consistency data from the die extrusion. We looked also at some of the contaminants that were there, moisture, looked at the FTIR. You saw things like large chunks showing up in some applications. You're able to compare the FTIR fingerprint to the baseline, and we saw some grease mixing showing up as well. And so the parameters were elemental iron, elemental silver, a little surprising, but it turns out there's a lot of silver in helicopters to help soften some of that, that fretting wear that can take place. So we monitor silver levels, silicon levels as sand and dirt. ferrous debris levels for the larger wear particles that show up, because the elemental iron is going to look more at the smaller particles.
Mm-hmm.
Moisture, the consistency values, and then we created an oxidation index. So we were able to compare greases that had one antioxidant and those that had two antioxidants
Right.
as a a complementary system. And so we created these kind of, it was a study we did. It was over 11,000 parameters were measured in the grease
Um,
samples from over 1,000 helicopters. And by looking at this, we kind of made this kind of, this sort of waterfall plot, but it's really just a plot from largest to smallest, looking at the silicon versus the iron and aluminum. And you can see it
mm,
track very closely silicon as a culprit, causing higher levels of iron and aluminum wear. Not surprising when you think
yep.
about it, but it's good to see that validated in the data. And then we were able to create an oxidation rating graph for all of these.
Mm,
And so you go from a top rating of 300, which would be a fresh new grease, all the way down to when it's only at about 50 for the oxidation index, which means that 3/4 of the antioxidants are gone.
mm-hmm.
And so by creating a line of best fit, we could project out what is that optimal grease replenishment frequency. And you can see here it comes out to be like 170 some by using this regression line of best fit. And so we use that as a key parameter. So here was the outcome of this study that looked at all of these different components: swash plates, engine adapters, drive collars, hanger bearings, fan shafts, and so forth. The majority of them were driven by that oxidation index. So we want to get the old grease out before it's shot, and the general driver is down to about 20%, 20-25% of
Mm-hmm.
remaining antioxidants. You want to get the fresh lubricant in there. So that was the driver there. And all these numbers are the number of flight hours that had you hitting that point. And some of the hours before this were actually quite short. For instance, the swash plates were at 50 hours. And you can see here, we got studies that took us up over 200 hours, right?
Mm-hmm.
Now, they decided not to go that far. The new time is, I think, 120 flight hours. But that's a huge expansion of
Mm-hmm.
what had been done before just by using data. And it's all data driven, using grease analysis to set the intervals to optimal grease replenishment. So most of the lubrication intervals were doubled. The final service intervals were kind of aligned with other maintenance tasks, which makes sense. They reduced the lubrication tasks from 98 to only 56 tasks per 1,000 flight hours.
Mm,
So almost cutting the workload in half.
yeah.
And accordingly, the amount of grease being used cut down as well. So the footprint is down. And then there was an average of 20 service interruptions per 1,000 flight hours. That was cut in half as well. So these helicopters are in the field more often. And this
Mm-hmm.
picture is taken from the Canadian Air Force, and that's a hospital helicopter. So instead of having to be grounded to have the grease replenished, it's now in the field more often, being able to help the people that need it. And the calculation here was 100 million annually being saved across that 1,500 helicopter fleet. $100 million saved by grease analysis.
A lot.
Yeah. So that's only one little slice,
I
right? We
know.
haven't even
Yeah.
gotten into wind turbines and power plants and paper mills and steel mills. Steel mills. Just don't get me started on
Mm,
steel mills.
yeah.
How much grease is used there? But let's summarize this. Electric motors, motor operated valves, the reliability and the life of these critical components can be optimized by leveraging the lubrication tools and using the grease analysis. The
Mm-hmm.
grease analysis can be performed either at the machine with the mini lab, or using in the field or using portable devices to screen that condition. And once we see that, then we can go to the laboratory analysis to get that more detailed understanding of what's happening, especially when we want to optimize grease replenishment. We probably want to look a little deeper, not just find the problem ones, but say, even the ones that are okay, are they optimal? Is there
Mm-hmm.
too much life left in the grease so that we should back off, save that labor component, save that grease until it's really needed? And then, of course, finally, we can find failure root causes, and that'll help us extend the machine life. And so these are the things that I wanted to share today. And so I, I I don't know if we've had any questions.
We have had a couple of questions, but I did not want to interrupt you because it was just so, the information was so good. And I'm like, yes, this is what we need. We definitely need to be talking more about this. Now, the first question that we had Hamza ask was about, is there any sort of valid grease compatibility chart? Like something that has been done that some people can use as a reference? And like, I know you talked about, you know, being able to actually physically do that test because that helps in terms of, knowing the environment, knowing what's going on as well, and knowing what else could be involved because sometimes these charts are like controlled testing, you
Yeah.
know. Yeah.
So what I would say is have a questioning attitude. If you
Mhm.
have a compatibility chart, the first question I would ask is what data was used to compile the chart?
Ah.
And this is where it falls apart when you do your Google searches. You find these
Mm-hmm.
charts with no lineage, with no background, no information about the testing that was performed. Out of those 17 charts, I found one that showed that a study had been done in 1990 to provide the data for that chart. And so then I asked the question, have grease formulations changed since 1990? Yeah,
Mm.
they've changed since
Yeah.
2023. So I would say, has testing been performed? If so, what is that testing? And then is it more than just the thickener? Because Hamza, if we want it, we truly are interested in compatibility. One grease is in the machine, the other one's coming along behind it. Then we have to be concerned about all three modes there, which is the thickener, yes, but also the base oil
Mm-hmm.
and the additives. There can be issues there. We could be diluting additives down so they're no longer effective. If a new grease doesn't have the additives that are needed, we could have additive interaction, which is a chemistry problem. We can have a base oil incompatibilities, just like we do with
Mm-hmm.
oils. We know
Yeah.
that, right? We know we can't take a PAG and mix it in with a SHC
Yeah.
PAO. So we have to have the same concern about the grease base oils as well. So base oil. Uh, 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 Compatibility, chemistry, but also viscosity. I've
Yeah.
seen like sometimes people send some greases
Yeah.
to me and they're like, "You do a compatibility study," and then I look at the product data chart and I'm like, "Well, the one grease you're giving us is 1,500 centistokes at 40 degrees C, and the other one is
Yeah.
68. So
Yeah.
no, they're not compatible. One of them must be wrong." So I'm not going to say there has never been a valid grease compatibility chart. What I would say to those who would utilize them or want to utilize them is ask those fundamental questions. How was the data determined? And does it look at all of the compatibility concerns that I have for my application? And if I'm satisfied, then I can use that and move forward.
Yeah. And again,
Otherwise, we need to
mhm.
test it.
Yeah, testing is like, I always agree with the testing method because that's what you see exactly what's going on. Like it uncovers every single thing. So even though you may go to like your manufacturer, like your OEM and say, okay, well, what is the grease chart? Because I know some OEMs also do grease charts with their compatibility stuff.
Yeah,
And sometimes that may be all more accurate to their greases.
right.
But if you're using different OEMs, they will not be the same. So that's a good thing to think about as well.
Yeah.
And yes, Hamza is talking about all of these different studies. It's true. Yeah, you don't get those.
That's right. That's right. I mean, I've had people say, well, I don't need to do a compatibility study because the supplier said
Mm-hmm.
that their grease works with the old grease. And a lot of times
Yeah.
it's like, well, if they said it wasn't, they wouldn't get the sale.
Yeah.
Um, really, truthfully, though, it's up to the asset owner to ask the
Mm-hmm.
right questions and say, show me the data. I
Yeah.
want to see the data that is going to cover my use case where I have this grease already in there and I'm putting this other grease on top of it. And if we can't get that data, we either have to test for it or we have to take that extra effort to clean the old stuff out because the problems that can come about through that mixture can be
Yeah.
substantial.
Mm-hmm. I know what your whoever is telling you about, yes, it should be compatible. They are not the ones handling your downtime or anything that goes wrong on your plants. So if you can do stuff in advance, make sure get that guidance before you do all of that change out. That helps a lot. Trust
Yeah.
me, that helps a lot.
Yeah.
And I think we had another comment come in, Rich. Somebody was asking about the ruler test and if that actually addresses the antioxidants remaining in the grease. That one came in a it didn't come in through
Oh,
this side. Yeah, it came in a weird way. Yeah.
okay. Yeah, so it's a good question,
Hmm.
and I'll tell you what one of the challenges there is the degree to which the grease is being mixed as it's being replenished. Because if you think about oil, if we lose oil over time and we're topping it up, that oil tends to get mixed completely in there. So the new additives then get diluted down through the whole volume that's there. When we add grease, there's more of a likelihood that the antioxidants kind of stay in their own little package over here unless that machine is thoroughly mixing it through. So what I have seen is there for there the tendency for there to be more heterogeneity in the
Hmm.
distribution of antioxidants, only because you don't have that nice kind of reaction kinetics that you get from oil,
Yeah.
where the stuff that wants to react gets a chance to hit all those antioxidants, that the grease kind of holds them in little pockets and packets and things,
Hmm.
so it can really trash grease in one area, and then a little pocket over here has a lot of antioxidants. Some applications, though, it becomes quite clear that it's really being thoroughly mixed, and it does work quite well as a tool. Like in those helicopter examples, we got
Yes.
very good statistics on that, with that linear regression line that we were able to create. But I have seen other applications where the sample is more heterogeneous, and then it's a little trickier when it comes to the.
Mm.
Yeah.
Yeah, that makes sense because like what I see a lot as well is that sometimes like grease has to stay in place. Like that's one thing we can't. That's its purpose. That's why it's so different from oil. It has to stay in place. So if it's staying in place, you need to be aware if it's getting contaminated, if you're starting to see those changes, like you mentioned earlier, wear metals in it, the changes of colors. Like those are the main things that you want to start looking at in advance because that's what can actually save your motors. And I think at the end of the day, we want to save the equipment more than anything else because
Right.
that downtime is not what we want in any form or fashion.
That's right.
So, and
But
I
but
like, yeah,
but once we have that, we can also take a good look at the optimization piece,
yes,
because a lot of
mm-hmm.
times we're wasting grease. The
Yes,
one thing I didn't mention in that study from the helicopters was that even though we extended out the interval for most of those components, there was one component in there that happened to be very close to the engine, that actually the frequency that had already been in place was not often enough. So we actually had to shorten one interval while most
um,
of them were extended. So we did save a
wow,
lot, but we were also then addressing one deficiency where a grease was
mm-hmm.
already oxidizing before that frequency of maintenance was happening. So uh, the optimization can go in both directions,
Right,
and
yes,
sometimes but we shouldn't be disappointed if we go to do an optimization
yes,
study and we find we got to shorten the interval. We're shortening the interval to protect the machine and get
mm-hmm.
more life out of the machine. That should be first. But then there are often those optimization opportunities once we've taken care of the machinery. So
Yeah, and I think that it is important to know that it goes both ways. Because every time when you do these sort of analysis, people are like, let's extend the life. That's gonna help us more. But shortening the life can help you even more
yeah,
because that can be the difference. And we're talking about helicopters in the air. So that can be the difference of, saving a life in some
that's right.
cases. So
Yeah,
very important.
sometimes in the absence of data, people will be like, "Well, why did we ever decide monthly greasing? Let's go to 2 months and see if anything happens."
Yeah.
Yikes! I hope
Ooh,
I hope I'm not on that helicopter, right?
yes.
But so regardless of what it is, if we really want to protect those assets, don't
Hmm.
randomly adjust frequencies just
Yeah.
hoping for the best. Use the data.
Yeah.
Go where the data tells you, and work towards optimization, like the Chinook folks did very successfully.
Yeah, and like I love that you're able to work with them and like that helps reduce their all of their emissions as well because
Yep,
that's a lot that we were talking about. Like a lot of information. And just going back to how you get degrees and being able to save on your carbon footprint. I think that's very important for all of us right now, especially if we're trying to make that change, consciously, moving in that direction. It's something to just be very mindful of. You can also help reduce your carbon emissions with degreases, optimizing your stuff. Always a good thing to think about as well. So I'm
Yeah,
glad you brought that up.
yeah, if anybody would want that, I could share those kind of calculations with you because
Mm-hmm.
sometimes, maybe a champion wants to do grease analysis, but
Yes.
they can't get the justification. And
Yeah.
often at the corporate level, that's the
That's
tool,
what you
that's
need.
the lever that we can pull. And so, being able to do that and say we project that we can save this much, that might be a little nudge that
It
gets us
would.
doing the right thing for our machines.
Yeah, and like that is very important. Like being able to get that buy-in, critical. So of course, message Rich. He's on LinkedIn, and because we have this live on LinkedIn, you can just go in and click on his stuff. So be able to connect with him on anything, any other questions that you may have. I know we may get questions after this session is recorded, just because of how it lives on LinkedIn, but we will get back in there and try and answer some questions as well.
Yeah.
But thank you so much for sharing your information with us today,
Yep.
Rich.
Thank you.
Always good.
Yeah, thanks for setting this up, Sanya, and I look for the next time. And again,
Yes.
if anybody has specific topics they'd like us to do in the coming sessions,
Mm-hmm.
let Sanya or I know, and
Yep.
we'll make that part of what we talk about next
Yeah.
for the Grease Thief.
All right. Thank you all so much.
All right,
Bye.
bye now.